Good afternoon. Thank you all for coming. Welcome to the Michael Korybalski Distinguished Lecture in Mechanical Engineering. I'm Conwell Wang, Department Chair of Mechanical Engineering. Well, this annual lectureship presents high-profile speakers that address the general theme of quote-unquote engineering in society. That is to promote the impact that engineers have on addressing large societal problems. This lectureship has been endowed by Michael Korybalski, Chair of the Mechanical Engineering External Advisor Board and former CEO of Mechanical Dynamics. I want to take this opportunity to thank Michael for his generous gift so this event can happen. So Michael, can you please stand up and let's give Michael a big hand. Thank you, Michael. Now it gives me great pleasure and honor to introduce our distinguished speaker today, Dr. Albert Pisano. Dr. Pisano is the Dean of Jacobs School of Engineering at the University of California, San Diego. He earned his PhD degree in mechanical engineering at Columbia University and was a faculty member at UC Berkeley for 30 years before moving to UC San Diego. At Berkeley, he held the Fanuc Endowed Chair of Mechanical Systems, was a department chair of mechanical engineering and acting dean of engineering. He has also served as a program manager for DARPA. Dr. Pisano is a world-famous leader in the field of micro-electromechanical system, MEMS. He's a co-inventor listed on more than 20 patents and has co-authored more than 300 archival publications. He is the co-founder of 10 startup companies in the areas such as MEMS manufacturing equipment, RF devices, and motion sensors. He was elected to the National Academy of Engineering in 2001 for his contributions to the design, fabrication, communication, and education aspect of MEMS. In 2008, he was named one of the 100 notable people by Medical Device and Diagnostic Industry magazine. He's a fellow of the American Society of Mechanical Engineers. So without further delay, let's welcome our speaker. Al.
Thank you. Okay, I got the green light from the little box on the hip which says the mic is working, right? Okay, we're good. All right, so hey, good afternoon, everybody, and I'm very, very honored to be here. This is a very prestigious lecture series, and it was very kind of you to invite me to be part of it. And what I'd like to do is to talk a little bit about my school, and then to talk about some higher level issues that engineering can indeed help us solve in the world today. And indeed, the theme for the talk is engineering as a force for the public good. And we know that by and large, engineers are all great people, but we're particularly at the Jacobs School, we're focusing our efforts on engineering specifically as a force for the public good, and I'll explain more what I mean about that. So first off, I have to tell you a little bit about where I'm from. Yes, 30 years at Berkeley, but I don't remember any of that now because I'm 3 years of 100% of Triton. What is a bear? A bear is something you poke with the stick that Triton holds, right? Or something like that. I don't know. It's, I'm not involved in that anymore. The real point is that our campus has these 8 words. You got to take a deep breath before you go through the whole list. We strive to be student-centered, research-focused, service-oriented public university. I'm one of the deans of the divisions there, and I make sure I toe to that line. More importantly, the school is doing pretty well in the rankings. If you look at this particular rankings, Best Globals, we rank 7. The school will be 17 in the engineering schools with a PhD program. But this is the fact that most people are totally shocked at. The Jacobs School of Engineering at UC San Diego, right now in this quarter, we're on the quarter system, has 6,677 undergraduate students and 2,244 graduate students. That undergraduate body is bigger than Stanford and Berkeley put together. It's bigger than Stanford and UCLA put together. In fact, it's bigger than any of those two put together. So this school has grown to be a big machine. It's got a lot of industrial support, and our job is to help supply talent, leadership, technology, and talent and technology to the region. Indeed, I don't know exactly how big University of Michigan is. I'm sorry, I forgot to do the Google search before I came. However, last year, my school alone put 1,600 engineers into the workforce. So there's a lot of industry people who come and talk to me and say, you know, if you don't get this right, you're making a big crater. So okay, no pressure. Thanks. I'll make sure I do it right. Oh, by the way, you're going to help me. Okay, good. The annual research funding is rising since I arrived there. This is 7% more than the year before. We're booking research right now at a rate that'll put us in about 5% higher than that. So in 3 years, if you can clock in a 12% rise in research expenditures, that's always a good thing. And the faculty in my school, there's a larger percentage of them, I think, than normal, that like seeing new inventions through to product. So we have a lot of startup companies coming out of the school, and a lot of faculty actually keep burrowing down to make sure it actually comes out at the end of the commercialization pipeline, instead of saying, hey, I worked the first principles, that's good, see you later, someone else can do that. So I like it down there. It's kind of like my style that I was in MEMS, and therefore it's okay. I'm in among a bunch of colleagues that are like-minded. So I hope as a dean we kind of get along, but you never really know until you finish with the job. I just wanted to point out that when we say as a force for the public good, as a force for the global good, it means that we see our inventions right out to a product, as I alluded to, and indeed these are our most recent success stories in the sense that they all got funding or they all went through a major IPO of one kind or another. Paul Martini, BS of Computer Science, founded iBoss several years ago. It's one of the fastest growing network security companies, and he just finished building a building for 200 programmers, and he put it across the freeway from the engineering school. So if I stand on a chair in my office and look through the upper part of the window, I can look into his office window because I visited him in his office and said, wait a minute, is that my building there across the freeway? And he says, yes, it is. So our companies love to mine our students for job opportunities, and we're grateful for his support. Christoph Schilling is an older PhD out of bioengineering. His company is Genomatica. He uses plant-based technology to synthesize long-chain polymers that we would normally get from petroleum. So wow, that's kind of nice. You use basically, if you want to minimize your dependence on oil as a feedstock, maybe you could grow the right plants that create that. And he was a bioengineer. He's doing quite well at this point. Two newer ones, Sarah Guthels and Raj Krishnan. Sarah Guthels is the CTO, came out of computer science. She is part of the founding team of ThoughtStem, which is a quickly growing computer course and training program, and especially noteworthy is one of their video games in which the mythological wizard travels through a medieval world, but when the wizard runs up against problems, the wizard has to write a piece of code in order to solve the problem. And I said, wow, that's pretty good. I wish I had that when I was going through my programming course. Sounds like a lot of fun, and indeed it is. And so Sarah's the genius behind that. And Raj Krishnan says, hey, you know, what if at the same convenience of a pregnancy test, or maybe more appropriate, a Lancet test for diabetes, you could find out if you have one of several common forms of cancer. Can you make a point of care cancer test that will use exactly one drop of blood? And indeed, he did the preliminary research in the bioengineering department, and he ran off and founded Biological Dynamics. And so these are quickly growing and up-and-coming concerns. And I'm sure every school has a similar set like this, but I just wanted to let you know that you know, we're in the thick of it when it comes to the entrepreneurial effort. Let's back up for 2 or 3 minutes and talk about a global issue, and then we'll dive down into particular projects. So I don't know if anyone here has read the book by Paul Diamandis, and I forget the co-author, apologies to the co-author, called Abundance. It was a pretty popular reading 2 or 3 years ago among all the corporate CEOs, at least the ones that I knew about, know. And the basic premise is this. I'm sorry for all this extra detail. I'll just cut to the chase, which is that this planet has a chance of shifting the supply and demand curves by somewhere near 2035 if we do a number of the right things. And by abundance, I'm saying, what if we could alleviate issues with food, medical care, clean water and air, and energy? What would we need to do in 20 to 30 years, in other words, in one generation, to shift the supply and demand curves for that? So I'm not going to talk about the sensors right now, but the point is that what industries would you have to launch? What industries would you have to generate engineers for? What industries would you have to clear the path for using policy decisions? What industries should you grow in order to actually solve that problem? And if you believe what you read in the book, and I like to because it turns out my school's got all these covered, the idea is let's look for exponentially growing technologies that will basically get into large markets very quickly. That the first impact is, of course, those companies will improve the quality of life in the first place. However, they will drive the global economic growth that we need in order to address many of the problems that these particular industries can't address. Now, it's not the panacea. I'm not going to say it. All you need is engineers. We all know that it takes many kinds of professions to make the world go round correctly. But I'm offering the posit that if you make big investments in biotech and bioinformatics, medicine, nanomaterials, nanotech, networks and sensors, and my favorite part is I think we're going to need about 45 trillion sensors in the next 20 years. Digital manufacturing, computational systems of other kinds, AI and robotics, you could argue how to divide those two. These are the areas that are really going to generate the big markets that we need to carry us forward from where we are now. And if you look at waves of technology, 20 or 30 years ago, all the computer operating systems companies matured. Okay, the next wave was mobile apps. Okay, now we're going through a wave of social apps. Okay, well, what happens after those waves? I think some of the next waves are going to come from this list. So we're doubling down on that list, and now what I'd like to do is talk about some of the new programs and new efforts we're having at the Jacob School. And indeed, when I arrived there in September 2013, I took a look around and I said, I really love my faculty. They're all strong performers, but there are too many of them that function as lone cowboys and not enough of them as larger teams. So we started a new program which I call the Dean's Agile Research Center. The Dean's Office puts in an initial investment to launch a center, which is a bottoms-up thing. The faculty have to come up with the ideas. I don't micromanage any of that, but we'll handle their media, their marketing. I handle their administration. And we have a schedule by which in 4 years the centers have to become self-sufficient, or, hey, I pull the plug and we move on to the next. So I thought that would be a controversial thought in a school in which most of the faculty prefer to develop their own expertise. And to my surprise, within the first 18 months, we have now launched 8 Agile Research Centers. And I've got 3 more in the box. And so this is the first one that was launched. Professor Joe Wang, who is now Department Chair of Nanoengineering, put together a center and said, hey, we're going to pull together everybody that's working on wearable sensors, all the way from hard sensors that are attached to devices that you wear, all the way to soft, flexible sensors that actually have the same compliance as skin. And so just a few interesting examples of what you can do when you pull that group together. This is the work of Darren Lapomi, who came to us from Stanford. He does intrinsically elastic semiconductors. The molecules themselves have aromatic rings or other things in it so that they are intrinsically elastic. We're not making a spring by winding wire to add compliance. The wire is intrinsically elastic on its own. And to show just how effective that is, what he's showing here is he has put an elastic solar cell taped onto an arm. There's the wristwatch. And we're doing a 50% tension compression. And you can see that even after 1,000 cycles, you know, the performance is the same as it was before. You just stretch it and come back, stretch it, come back, stretch it, come back, and it's still performing with the same output. So we have become very, very deep in molecularly stretchable electronics. And if you know the San Diego region, you might say, yeah, you got great beaches, good. And you got the Navy there, biggest port in the Pacific, by the way, bigger than Manila or Hawaii, good. But we also have one of the biggest biotech arenas in the country. We're the first or second biggest. They call it the Mesa, which is the large flat rock formation just north of La Jolla, just north of the campus, where there's a huge phalanx of biomedical research, right? The Salk Institute is there, Sanford Burnham, all these places that really do a lot of biotech. So if you look at the fact that, hey, you know, you can start talking about skin level stretchable electronics that humans can wear, this has a big application in the biotech industry, biomedical industry. And indeed, if you come and visit, you can come visit this mannequin, which stands at attention, or more or less a San Diego style attention. You know, kind of like surfer dude, maybe I'm paying attention to you attention. And he actually displays a whole bunch of technologies, including temporary tattoos that will measure pH, or metabolite sensors that actually can measure the lactate in your sweat. Because you may not realize your sweat glands are filters, but they're only 98% efficient. So all you need, and I'm saying that sarcastically, all you need is something 50 to 100 times more sensitive and 50 to 100 times less expensive and elastic and something that can run on a couple of, oh, I don't know, maybe 100 nanowatts. And hey, you got a functional sensor. Sounds like a tough set of technical projects to us, but we're making a lot of progress on that. And indeed, this is one of the areas that we're concentrating on. By the way, you don't have to put all this technology on skin. You can put it on latex rubber, and then you wear gloves that have sensors that are detecting for you know, deleterious chemicals deleterious to your health. This photograph has not been touched by Photoshop. This is an actual photograph. There's no mock-up here. The infant you see on your left is a premature baby in an intensive care unit, and the infant you see on your right is one of a set of test patients in 4 hospitals in which the work of Todd Coleman, is already in test with. And the sensor you see on the right includes stretchable electronics, an antenna, some very low-speed circuitry, and we're actually making metabolic measurements on that infant, as you see in that picture. This is not, what are we going to do in the future? This is, he put these first versions of this out 8 months ago. Now, you know, you're in a biotech hub and you start showing stuff like this around. Now you got people talking entrepreneurship left, right, and center. So, okay, I think we may be hitting a home run on this one. And, you know, the untold story here is that each of these adhesive patches are only good for so long. And there's a regimen by which you have to take the sensors off to let the infant's skin heal. Now, look at the size of the adhesive patch, look at the size of the kid, and ask yourself, how many times can I move that before I run out of fresh skin? And that's actually a big problem. One of the problems with instrumenting up an infant is that you get all sorts of skin infections, which you just add to the list of things the poor child is suffering. So we're seeing a lot of push to move in this direction, and indeed we're galloping forward as fast as we can. So this is a close-up of Todd Coleman's work. This is an actual functioning sensor. I think this one is measuring lactate as well. And you can see that you can squeeze it or stretch it. 50% strain is no big deal, and it remains functional. And the early work was published out actually in 2011. So we're in hospital trials right now with this sort of thing. So there's a very direct one. Hi, we're going to do something that people are going to feel the difference about immediately. And I'm very pleased. So let me shift a little bit and say, well, it's one thing to make all those lab prototypes. And so how are you going to make 1 trillion of those? You know, 1 trillion's a big number, man. You know, I know that, you know, astronomical units come in, you know, groups bigger than that. And yeah, you can count molecules and do Avogadro's number, but you know, 1 trillion is pretty big. All right, you know, 33 million cars a year made in the world, that's a big number. 300 million people in the country, that's a big number. 900 million cell phones manufactured last year. Whoa, that's a big number. But that only gets you to 1 billion. So you imagine if everyone who bought a cell phone actually bought 1,000. Imagine the size of a pile of 1,000 cell phones. All right, that's 1 trillion. All right? It's too easy to talk about big numbers, so let's talk about, you know, boxes of cell phones following you around. That's a big number. All right, so what are you going to do? What are you going to do if you decide you want to make 1 trillion of something? So I say we're going to print them. Now I know there are many, many people looking at many, many different ways of printing. But I'd like to spend a few minutes talking about how you might print them in an alternate way. And I'll give you the punchline. It's 4:30 exactly. I'm going to finish at 4:50 exactly. And I'll tell you the answer right now, and then we'll go, I'll show you enough slides to make you believe me. So the way to do it is, one, you're going to use an ink stamper in which the ink flows into the stamper after you put it in contact with the surface. Second, you're going to keep all contact pressures at 1 atmosphere or less, because I'm not going to spend a lot of money creating pressure. Third, no temperature in the process ever is going to go above 60 degrees centigrade. And I'm going to print up to 4 inks at once with 1 stamper. Put the stamper down, print 4 inks to do 4 well-registered features, and then take it off. Oh, by the way, when I take the stamper off, the ink is dry. All right, now if I got enough curiosity out of you for that one, I'll skip through a couple of tricks about how you make that happen. Oh, by the way, the secret solvent that we use to make all this miracle occur is called water. So every ink that you see here that does all the stuff that I say we do, it's basically it's a nanoparticle colloidal solution in water. So we don't even worry about fancy volatiles that we have to capture, you know. So this whole thing is set up for how are you going to drive the manufacturing cost as far down as possible. No pumps, no big presses, no big heaters. And oh, by the way, it just gets humid after a while when you print enough of this stuff. Okay. So, yes, you can talk about printing interconnects or sensor components, structural sacrificial materials, or various device components. What we're focused in on is let's print with nanoparticles and polymers. And remember, the solvent for all of this stuff is water. So yes, we can talk about the genealogy of printing. And I'm not taking anything away from any other method because they all have special uses. I'm saying that I'm betting my money on template-based printing. And under template-based, you see things like gravure, nano-imprinting, or maybe micromolding in capillaries. Gravure is a great process for doing very fine, very accurate structures, right? But if any of you have ever done it, you realize that in gravure, you're spreading the ink first, you're taking a hard stamper, and you're crushing it down at great pressure in order to push the ink away from where it shouldn't be. That means you always have a cleaning step, which reminds me, I forgot to tell you, in the process that we're using, no cleaning step either. So you don't have to, it's just done when you lift the printers. Stamper. Manufacturing guys kind of like that, and I figure in this town, you guys understand what manufacturing guys like, right? Okay. Yeah, is it like I just touch it and wait and take it off? Yeah, it's done. Good. I like that. Let's truck that into the factory. So the game is the following, and again, here's the innovation that we did. So you take a substrate and you take a template, but the template is either PDMS or PNP, a permeable polymer. So all stampers are soft permeable polymers, and the first thing you do is you soak the template and the surface with the water. No ink yet. You assemble everything wet. So you do a complete wet assembly. There's no air anywhere. Then after you make contact, you apply nanoparticle ink here. You can just puddle it at the side, and it will naturally fill the mold. And everyone would say, oh, right, capillary transport. The answer is no, because everything's wet. So there is no meniscus. So it's not capillary transport. What you're doing is you're evaporating all the solvent out of the permeable polymer, and it's actually a negative pressure process. So all your thoughts about laminar flows and capillary limits, no. We're going to dodge all those things. And then what you do is you just make sure everything stays mildly warm so that the evaporation goes fast enough. And if you take it off too early, you get this. And if you take it off a little bit later, you get that. The question quickly becomes, what can I use to get the water out of there as fast as possible, right? We're engineers, we're pulling the, you get an idea, now you start peeling back the onion. Okay, wet assemble, yeah, but I want dry disassemble. So I need something that gets rid of water right away. And what's the best way to do the patterning process itself? So if you take a look at available materials, every MEMS guy is going to jump immediately to PDMS, polydimethylsiloxane, otherwise known as General Electric tub and tile sealer. And the solvent for making that, and the solvent for making that liquid, you spin cast it, is ammonia. So if you can stand lots of ammonia in your lab, you basically dilute silicone rubber tub and tile sealer, and you use that as a MEMS microfabrication material, and it works fine. Except that, and these are the typical permeability numbers. So for example, 4550 for carbon dioxide, oxygen, and nitrogen. And why am I looking at these? Well, these are all permeabilities that would be similar for water, and this is easily available published data. All right, I'm going to bring your attention, we'll cut back to this in a second, I'm going to bring your attention up to this PMP, which is poly-4-methyl-2-pentane, and this is extensively used in the petroleum industry. This is what the gas processing guys use to purify gases. This is what you get your 9 nines or 5 nines or 6 nines purities out of by using this material. Now you can't buy this anywhere, you have to synthesize it. So I'm making an allusion to a little bit in a minute or two. I'm going to tell you that we had to make our own in order to get to the next level of the project. So in any case, we took a look at these materials. PDMS works just fine, and what we're showing here is that if you keep pooling nanoparticle ink here at the left, and we're using densities of about 1 to 2%, so it's very dilute. The organic solvent equivalent of this would be lacquer, right? Mostly solvent and a little bit of pigment. So we're using very, very low density inks, and we're just waiting for the particles to pile up in at the end of the capillaries, and then as the solidification front travels back, then you're basically doing your printing. Well, is it any good? Sounds like, kind of works in course mode. Let's just see how far we can push this process. So for example, you notice the first thing I'll show you is that using the same stamper, you can change all the chemistries around at will. So for example, we're going to print gold nanoparticles on polyamide and then gold nanoparticles on glass. No big deal. The interesting thing is this is an absolutely clean, we use this pattern to show that you do the printing, there is no cleaning step, and you cannot find gold nanoparticles on this place. Now, gravure guys have a hell of a time doing stuff like that. And if you look at the cross sections, you say, well, it's not perfect, but boy, that's pretty good for a soft stamper. That's a 4-micron size reference there. That is a 5 or 6 micron high printed structure. Now, that's not easy to do with printed materials either. Well, what other things could you print? Well, how about PMMA on silicon, or how about a cell culture on glass? How about if you want to print PVDF, a high breakdown voltage polymer? Or how about chitosan on glass? Now, chitosan is an interesting material. Chitosan is the material, well, chitin and chitosan, they're two versions of the same material, is what nature uses to make butterfly wings, beetle shells, shrimp shells. By the way, it's a very good, so it's the structural material of the insect world. Humans use collagen and calcium, and plants use cellulose. Chitosan is also widely available. It is used to take heavy metals out of water. It's a filter material. So I'm hop, skipping, and jumping through this, and you would say, oh, it sounds really good, but I got a question you can't answer. How do you print a single dot? Not everything is a line. And so the answer is, well, you print twice. What you do is first you print the template. So we're going to print dots now. First I'm going to print the lines. Then I'm going to scene here. Then I'm going to put a drop of the nanoparticle ink on it, and it dries and the particles assemble. We're going to use a secret template removal system called Scotch brand magic tape. It pulls off the unattached particles, but the ones that got through the template and touched the surface, they're bound by Van der Waals strong enough that Scotch tape doesn't pull them off, and bingo, you have yourself an assembled structure. And here's some examples. Now we're printing zinc oxide nanoparticles on silicon. Iron oxide's a little tougher because we didn't solve the shrinkage problem. We'll have to go back and tackle that sometime. But just as a quick test, yeah, it looks pretty good, but not perfect. Well, what if you want to print multiple inks at the same time? Well, then you have multiple channels. So here's an example. How about cellulose acetate and ABS plastic on glass? How about cellulose acetate and PMMA? How about gold nanoparticles and cellulose acetate? So simultaneous printing with a soft polymer and extremely good registration. I used to work at Xerox before I went into academia. I actually worked at General Motors and Singer sewing machines as well. Anyone need their sewing machine adjusted? I'm still good at that. The real point is, hey, you had to learn, man. It was the old days. Hi, first you're going to learn about everything we ever built, then maybe you're good enough to do something new. Anyone remember that? Okay, yeah, so I went through that hazing ritual. It was a good one, I guess. The point is that these are all well-registered features. If you look at the size bars, 100 microns, 100 microns, 500 microns, zoomed out version there. There's a 120 at the top. So these are all, 10 micron lines. Can you push it? Can you go further? Well, I'm going to skip through some of the theory, which says, yes, we did do the PDEs. Okay, fine, single, one-dimensional analysis to be able to compute the solidification front. So yes, just like plastic injection molding, you got to size all your sprues right to make the flows are right. Okay, we do that. We built all that up. We accounted for velocity gradients. The particles don't diffuse with respect to the bulk flow. They're too small, so they're trapped with the liquid. We did the mathematical modeling to develop some dimensionless parameters for how to pick the right concentration and how to look at the right time. And it turns out that, no, don't worry about diffusion. The particles just go with the flow. The mathematical modeling lays right on top of the theory, the theory lays right on top of the data, so we're very happy. And these are test structures where we predict how far in we will solidify structures as we go. And that solidification front is fairly well defined as it goes forward. We looked at velocity, the fluid velocity versus concentration, and so we have optimum curves for where this knee in the curve is going to be your sweet spot. That's going to set your ink concentration levels. And we even looked at pressure losses in the channel, not a negligible, under certain circumstances, non-negligible, but mostly negligible, and we actually found an optimum ink concentration to trade off long patterning versus template distortion. let's cut to the chase. Yes, we looked at the pressure effect on the PDMS. And the reason why we started really looking at this is that we noticed that, you see that feature that I said, yeah, it's kind of okay? For a long time we said, wow, we're getting partial filling. We don't understand. Why would the particles want to go to the bottom in a regime where buoyancy just doesn't matter? So why do we always have, do we have an air bubble? What's going on with this? And so finally we ran a calculation and said, hey, wait a minute, the PDMS is collapsing due to the negative pressure. This is subatmospheric here. The fluid is being pulled in, not pushed in. So this is actually the shape of the PDMS as it's, and we checked the mold, right? Oh yeah, pieces coming off in the mold. I don't see anything here, what's going on? So we finally said, all right, that's it. This PDMS works pretty well, but not as well as we need to. Let's go one step up and look at this poly,4-methyl-2-pentane and look at the fact that it is much higher in permeability, and that means faster evaporation of the solvent, and that means the printing speed goes up. But what really blew us away, and maybe the chemists in the group or those who know chemistry would appreciate this better than me, but I was totally shocked. You can get a material that is 1,600 times stiffer and still have huge increases in permeability. So the elastic modulus for PDMS is basically not even 1 megapascal, but for PMP, it's 1.6 gigapascal. So the mold material is 1,600 times stiffer and more permeable. So hey, so we redid all the calculations. All right, water's going to be moving this thing a lot faster. The flow velocity is going to be increased. You redesign all your sprues. We lock on to this. But unfortunately, you got to synthesize it yourself. So I had a student who was good at chemistry. We made our own spin casting system, synthesized the material from the precursors. I won't go through the multiple day filtering process that we had to go through to make it nice and clean. We even did the infrared spectrum to make sure that we're synthesizing the right of many forms of PMP. And what we do at that time was print a square centimeter at a time. And here's our first test structure. And so what you see here, this looks like a bunch of test bars, but what you really are seeing is a feed sprue, another feed, another feed. And if you look in the center here, now you're looking at these features that are submicron. That is a 900 nanometer feature that we're printing. Now at this stage, we got obsessed with going to 400 nanometer features. And since the contract is over and everything's free and clear, I'll share a little secret with you. A bunch of saw filter guys saw this and came and approached us and said, we're getting our clocks cleaned by the F-bar guys. Now an F-bar is a film bulk acoustic resonator. It's a piezoelectric material that vibrates in thickness mode up and down. You can drive those to 5 gigahertz, no problem. And they took over the cell phone industry because the saw filters are the guys that use interdigitated electrodes to launch a piezoelectric wave laterally, catch it on the other side, go back to electric, and perform the filtering function that way. No saw filters go to 5.6 gigahertz. So all the new communication protocols are killing the saw filter industry. So two different saw filter companies came by and said, you know, we kind of saw this paper you published. We're willing to take the research next step. Can you get down to 200 nanometer lines? Because as soon as we get to a 400 nanometer pitch, and we use, I forget what it is, indium niobate, the piezoelectric material of choice for saw filter guys, we're going to claim, we're going to get to 5 or 6 gigahertz, and we're going to take back that saw filter market. So son of a gun, economic interests and a real live company said, hey, we like your paper, so let's see where you can take this next. So now we started doing, all right, now this is getting real. The line's got to be really straight. The pitch has got to be very accurate as well. No more swelling anywhere is allowed because, you know, your dispersion goes up as your, you know, if the pitch is different as you go along, you get a lot of losses. Your Q goes down in a filter. So now we got a filter aspect we're going to. And So now we're starting to compare PDMS with PMP. And remember, we're using the same pattern with the sprues readjusted for the flow rates, printing the same features. So this is a printed cellulose acetate on a silicon substrate. Look at the straight sidewalls in a printing process. That is a 5 micron high block. Whoa, you could start doing transistor junctions on, primitive transistors with that. This is a interdigitated pattern. And then when we took our test structure, you notice now here we go from, here's a sample of our test structure, down to this size. That's a 3 micron length reference. There's a 1 micron. These now are 800 nanometers across. And that's starting to push the limits. Okay. We put silver particles on polyamide, gold nanoparticles on silicon. Everything's looking good. We're particularly proud of this result. These are 500 nanometer wide printed lines, nice and straight sidewalls, about 80 some odd degrees. All right. So let's end in 1 minute and 41 seconds on roll-to-roll patterning. So now you want to go fast. Oh, by the way, shortcut to today are we print 6 inches by 6 inches. We now make PMP sheets 6 inches square. We print as big as a 6-inch wafer. And that's all because of the low pressure stuff. But let's jump to what the real future is. Hey man, we got to make a belt, right? I mean, that's really the way to do it. So we did a quick prototype. We took aramid fiber belt, infused it with PDMS, and then on one side infuse in PMP in a spin cast process and molded it at the same time. This is that crude piece of belt. This is that's a 1-inch square sample of stamper. And these are the things we print with the belt. I mean, wow. I mean, remember, now you're rolling this back and forth on a cylinder to mimic a web process. So you are attaching and detaching. And even with that, look at what you got going. Let's just go straight to the money shot. There you go. That's a 5 micron. Look at the straight sidewalls on that puppy. That's looking really good. This is a 25 micron size. These are small holes in a sheet. We're printing this part, not the holes. And then these are 50 micron lines. That's pretty good for a first cut. These are first experiments on the belt-to-belt, roll-to-roll stuff. So I'll just show one application. Yes, you can print gold. You get 3% of bulk conductivity. And yes, you can print 2 inks at the same time. This is a fully functional UV light sensor using zinc nanoparticles and 2 gold electrodes where the feeds come in from the side. So that's an actual printed device. We took a look at engineering for the public good. There are a myriad of projects I could talk about. I zeroed in on completely elastic, completely stretchable, wearable sensors that are going to be a very, 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 very high volume market, but need to penetrate markets where people don't have a lot of money. If you really want to have an impact, you got to drive the cost down. If you're going to do that, you're going to make a lot of them. And if you're going to make a lot of them, you need a new kind of printing process. And why do you want a printing process that is as detached from the chemistry of what you're printing as possible? Because when you print chemical sensors, you need all kinds of different compounds. And I don't want to be in an ink formulation game. So what if all the chemical sensors you need can be synthesized, their reactive catalysts or whatever, could be put into nanoparticle form. You do an attachment molecule to stop them from agglomerating, and you just print any one of a number of chemical compounds you want as easily as you print different colors with an inkjet. But you're going to need straight sidewalls, and you don't want it to be a high temperature or a high pressure process because you're going to print on plastic or a whole bunch of other things. And you certainly don't want to have to add a lot of heat because that's just going to drive up the cost, and you don't want a vacuum chamber as well. So if you strip away all of that and let the transport processes do for you what you need to be done, and you can use an easy-to-find solvent called water, I think maybe you got a shot at really moving things forward. So thank you very much for your time and attention, and I appreciate the invitation to come today and speak.
time for a couple of questions. Questions from the audience?
Hopefully there's at least one. Or else I've either been totally transparent or opaque. Yes?
Yeah, in your list of things from abundance, which I guess is part of your
Premise.
plan for solving future problems, I didn't see energy there. Now, maybe you're going to address it through the sensor networks to improve the grid and other things, and maybe the biotech is going to bring us new feedstocks. But most of what I've read suggested we're going to go to war over energy and water in the next century, and that wasn't in your list. So is it embedded in there, and if so, where?
Yeah, so I'm negligent in putting in any major energy projects. I mean, I could have. The school certainly has a number of projects and new battery technologies and stuff like that. But for the sake of time, I thought I would focus on one thing, just sensors, because I'm a sensor guy, and talk about a manufacturing process that shows how you get from one end to the other. But I concede the point. Yeah, energy and water are going to be sources of conflict, and yes, they need to be done. We're doing things moving in that direction, just didn't report it.
But in abundance, what, did they address those resource limitations?
Yes, I mean, you know, it's a 300-page book, and I basically synopsized what I found on one page. So yeah, all of that is well embedded. Where I think we're differing is the industries that I listed are I didn't necessarily write the energy industry or the water purification industry. What I wrote down was a list of industries that have a chance of having meteoric growth that will generate new financial revenues that you can use to solve the other problems. So, you know, that's really why those industries were chosen.
What kind of sustainability do you have with these materials over time? I mean, you have an elastic sensor that's going on. Do they break down in UV light? Do they break down in different atmospheric conditions or contact with skin and so forth?
Right. So the answer is yes, of course they break. The trick is, do they break late enough to be useful? So for example, you know, on a chemical sensor that you put on infant skin, you know, that's good for a couple of days. And then, you know, you got to take it off the skin because you've been working chemistry on the surface of the skin. So if you need something to run 100 hours, that's actually a big deal. And if you can use a low tension mastic because you don't have to hold a wire, then you don't damage the skin when you peel. You know, it's like Post-its on your head, right? That's a lot easier than pulling off super glue. So, so therefore, if you design it right, you relax the longevity conditions and then use that to drive down the price. Other questions? All right, go ahead.
Last question.
Oops. I'll get you afterwards.
One of the features of the Agile Research Centers was their multidisciplinary nature. So I'm wondering, does that emphasis on multiple disciplines manifest itself anywhere in the curriculum in your degree programs?
Right. So for the undergraduate degrees, and all the departments have a number of different programs that they go forward with. And so I'm not exactly, so you're saying, well, let me go back to the question.
Is there an emphasis on multidisciplinary education?
Yes, of course.
Among your
Yes, so so we're revising the curriculum. We've put in a new experiential engineering track. The freshman year is characterized by people in their disciplines having hands-on experiences. But as they go through the sophomore and junior year, they have the option to go into experiential engineering tracks from other departments. And the whole thing is to prep everybody for their senior capstones better than ever before. So in terms of hands-on stuff, that's in the sophomore, junior year. The curriculum is being built as we speak. That is a piece of it. And the new research labs that we're building themselves are highly interdisciplinary, so your research experiences for undergraduates are intrinsically putting students into these multidisciplinary fields. And if you look at the centers themselves, you know, I have a chemist, you know, a bunch of EE guys, a bunch of polymer people. You know, you can see just the centers themselves are intrinsically multidisciplinary. Thank you.
Well, Al, before we let you go, on behalf of the department, we want to present you with a small gift. Thank you for coming and giving such an inspiring talk. And we want Michael to do the honor.
Now this thing, I believe, comes in 2 pieces, which I found out the hard way a few years ago. So what we'll do is we'll just start with this piece, and I guess they would like us over here.
All right. Okay, good. Thank you.
All right.
I appreciate that.
And a poster. You probably don't have any space on your wall for one, but
No, we'll find one. That's a very nice poster.
thank you very much for coming.
Okay, Michael, I appreciate it.
The force and the energy of that impact are transmitted to the helmet, to the surface of the helmet. That impact is transmitted through the helmet as a pressure wave or a stress wave. It eventually enters the skull and